All right, so we're going to work on something called optimization problems. You've been doing that already. So optimization problems, an optimal or the best solution, that's what a lot of engineers do. They have a problem, and they try to find the best solution. What they're finding in calculus is within a domain, the absolute max or absolute minimum. So if you know how to figure out the absolute max and absolute minimum within a domain by taking the derivative and making it equal to 0 and solving it, you're not going to have a single problem with these types of problems. What is probably the most difficult part of this is coming up with the equation in which you're going to take the derivative. Does that make sense? And so I'm going to go through some problems, and then we're going to do AP problems that focus on optimization. Okay, that's where we're headed. So what I have here in my notes is I say optimization problems are problems which involve finding the maximum or minimum point, the turning points of a function. If you review turning points of a function are relative of maximum minimum points, the tangent lines at these points are horizontal and have slopes of 0. That's what everything's been based on. And here's a very common one. Some object has this formula. You remember this formula? The negative 16t squared. And then I have a number plus 5t plus 20. Describes the height of an object if an object is released with an upward velocity of what? What would it be if I give you this formula? What is the upward velocity? 5 what? 5 feet per second. In other words, this is in the form of h of t equals a negative 16t squared, right, which comes from the gravitational constant, plus the initial velocity times t. It's positive if it's going up. It's negative if it's going down, plus the initial height. If it's from the ground, the initial height is 0. And it says from the initial height of what? So from this equation, what would the initial height be? 20 feet. And so what I said is one of the ways we can do this. Now, I'm always a little nervous about giving a table and giving a graph. I always use a table and a graph to help myself solve these problems, but I can't use a table and a graph in calculus as work or an explanation of why I know something. Does that make sense? I can refer to it, but I can't use it as work or a justification. So what I did is I put some numbers in here. And what I did is I just put 0, 0.5, and 1, because if I go up to another, if I would have went up to 1.5, it would become negative. So I only use those values. And I create a graph that looks like this. And I graphed it on my calculator. And I went here, I went 10. Right here, I went 20. And when I graphed it, I noticed, and it's going up, correct? Right? Because my initial velocity is positive. So when it leaves this initial height, it's going to rise for a little bit. Would everybody agree? And so it rose up for a little bit, and then it turned around, and this is kind of a bad graph. Turned around to look like that, but it was more parabol-like rather than all these squiggles that are in here. So who's ever watching on the internet, I apologize for that. That's really a bad graph. Notice there's going to be a place here where I have a horizontal tangent line. This right here is the maximum. Would you agree? The maximum height. The optimal height of my object. Does that make sense, everybody? The word optimal could be a maximum value. It could be a minimum value. And we'll get to problems of where it's a minimal value in a bit. Notice that the greatest height, it can be found by taking the derivative. So I took the derivative, and when I take the derivative of h prime of t, another name for that, read, is what? I'm not sure. Okay, this is time right here. This is distance right here, or height, correct? So distance divided by time. So what I do is sometimes give myself a hint. I look at those units. Okay, what do we call distance divided by time? Have I told you the story that I was watching Ellen when I was working out? Okay, because she's on, okay? And sometimes you don't have a choice of what you watch on TV just because there are other people around you that in the city and have a higher priority than yourself. So Ellen's on, and she's doing a game show. And here's the question. And this is a hint to this problem. You are driving 43 miles per hour. There are two women. You know, it's kind of like who's going to get the answer first type of thing. You know, kind of like what we did in the weekday news is Mrs. Burnham. Yeah, there should have been a question on that, okay? You may want to think of math questions just to see, okay? Here's the question. You are driving and your car is on cruise control at 43 miles per hour, okay? Here's the question. How far did you drive in 1 hour? And they looked at each other with panic. And seconds went by. And Ellen put her hands like this. The winner said this, I'm not sure, either 45 or 43 miles. And because they only had so much time, you know, in the show, she got it correct. So, distance over time, that's a what? Speed, okay? Now, another name for speed. Speed is the absolute value of, right, speed's always got to be positive. It's the absolute value of what? It's something that gives us speed and direction. Velocity. So the derivative here is the velocity function. Okay? And I got a negative 32t plus 5. So that gives me not only the speed, but the direction at any particular time, correct? And since it's the derivative, I'm going to make it equal to 0. Because momentarily, whatever this object was, it pauses and heads in the other direction. It kind of hangs up there. And then I get 5 over 32 seconds is my time. And then to figure out the height, I plugged in, oh, by the way, 5 over 32, I figured that out on my calculator. It's 0.15625. And when I plug that in, 0.15625, I got a height of 20.391 feet. So it goes up a little ways. Goes up about 4.8 inches about. A little bit less than that. Now, this is calculus, right, Maya? Now I'm going, because guess what? I'm not always a confident person. I see it in here because I've done the problem. That's why we have meetings at school. So I can do math problems in the meetings. Okay? Turn it on. Go to menu. Come over here to graph. Delete this thing. Put in a negative 16x squared plus 5x plus 20. Go to my window. Go from 0 to 3. And go from 0 to 21 by ones. Exit draw. And there it is right there. And then I'm going to see if I can find the maximum. And you guys know how to do it on a TI, right? I've showed you. That's, right? It's a function that produces feet. That's my optimum height. That's my highest height. Does that kind of make sense? All right. This, number 2, is my favorite all-time calculus problem. Because one of my jobs, Sawyer, at Kruger Welding was making trays, metal trays. I know from working at Kruger Welding, there are 231 cubic inches in a gallon. Because we had to make stuff for farmers in which animals would drink out of. And so you know how you measure inches and you could figure out how many cubic inches were in a particular shape? Well, the farmer doesn't want to know that there are 5,722 cubic inches that it holds. You have to tell it how many, you have to tell him or her how many gallons it holds, correct? We didn't have a calculator, so we had to do it by hand. But we only had to tell them 5 or 6. You understand what I mean? Or 10. So what we did is, and I'll draw you a picture, and I'm going to show you the steps. What I'm going to do is, first of all, it says an open box. I want to, an open box of maximum volume is to be made from a square piece of material. So we used a sheet of metal. Okay? And a sheet of metal looks like this. And it's 20 inches by 20 inches. And it says 20 inches, a square that's 20 inches by 20 inches on a side, by cutting equal squares from the corners. So we would cut these squares like here. And we had a thing called the nibbler. It probably had a real official name, but my dad called it a nibbler. And it would cut the metal in little pieces of chunks. All right? And so then what we did, it would look like this. And this is me attempting to draw. Okay? It would look like that with them gone. Does that make sense? And then we had a thing that would bend it up. And so we would bend it along here. And we would get a three-dimensional shape that would look like that. It would look like a tray. Does anybody know what brazing is? Okay, it's not welding. You get a torch and you get some metal, and it's for lighter metal. Okay? Yeah, kind of. Soldering's very, very light. This is kind of like between soldering and welding. Yeah, exactly. Okay? But we'd have, you see a lot of, if you ever go to an arts place where they make stuff right in front of you, like glass blowing, and sometimes you'll see metalworks people do some brazing. Okay? Use bronze a lot of times to do that. So anyway, does my picture kind of depict what's going on? So we're going from a two-dimensional shape to a three-dimensional shape. Okay? That's the real part of it. Now here's the math geek part of it. When you're asked to maximize something, the first question I'm going to ask myself and ask you if you need help, what is it that you're trying to maximize? What does it say in there? Jeremiah, we're trying to maximize what?
Space. Volume.
Right here, volume, correct? So I'm going to write V. So I look at this shape from geometry, How do I figure out the volume of that shape?
Length times width times height.
Okay, this in AP Calculus, they think you should know how to figure out the volume of a rectangular prism. Length times width times height. Okay? This is not helpful in calculus because I'm going to take the derivative of that and I don't want to. Because it has icky product rule all over it, right? But this is called the primary function because that's what I'm going to take the derivative of. Does that make sense? So I got to come back to my picture, and I want to create my volume equation so it's a function, and I'm going to write v of x. I always use x as my independent variable. You don't have to. I like to. You know why? Because x is in my calculator. Okay? So I got to get back to my picture, everything that's in terms of x. So I looked at this. The volume of this is dependent on the size of the squares that I cut out, correct? I mean, I could cut them out this big. Now, it probably wouldn't be a good idea, right? But it's kind of dependent on how much I'm going to cut out. Would you agree? And so what I did, I said, okay, this, and it's, since they're the same size, those squares, I'm calling those squares x by x. So this distance is x from here to here. Would you agree? And it's x from here to here, right? It was 20, so what's this length right here? 20 minus what? I think I heard 20 minus, and then all of a sudden people got afraid. 2x, because I'm taking away 2 x's, right? Minus 2x. So in other words, this is 20 minus 2x. This also is 20 minus 2x because this shape was a square, correct? What is the height of this? What is it, Nick? X. So now this is my length, this is my width, this is my height. So now my volume becomes this. X times 20 minus 2x squared. Would you agree? And I'm going to take the derivative of it, right?
That should be 2x right
Oh, I wrote x, it should be 2x. Correct.
now. No, in that second parenthesis.
Oh, right here. Like that. V of x equals x times 20 minus 2x. In case somebody walked out and got a snack. Right? That's watching. Maybe, you know, had breakfast. A donut. Went to Holiday, picked up a donut. Wondering what in the heck happened. That's probably. Okay, so this is going to be v of x. Hey, are those little kids watching on daycare? No. The people that were second period, we did a shout out to the daycare people that his mom runs, just in case. You know, they might be really bright. 400. 2 times 20 is 40. There's 2 of them, 80x. Plus 4x squared. Does that look good? The way things are going this morning, I wouldn't be surprised that I made a mistake. And since v of x is equal to 400x minus 80x squared plus 4x cubed. Does that look correct? McKenna, does that look correct? No errors? Alrighty, now, let's flip to the back side. And I know the bell's going to ring here shortly, but I want to talk about what's the domain? of this shape. Can I put any number that I want in here? Could I put negatives? No. Nor would, I don't know if even my dad knew what a negative number is. I should have asked him. He would say, hey, and I would say, hey, it's like below 0. And then it makes sense to him. Could I put 0 in there? No. So would you say that x has to be greater than 0? Could you see that if I put it in the function here, I would have a problem with 0, right? I would get no volume. So my domain, 0, I know x has got to be bigger than that. Can I make it as big as I want? It has to be less than what? 10. How did you get 10 and not 20? Because you took 20 divided by 2, right? If this comes 10 this way, it would have to come 10 this way, correct? And you'd be left with a little dot here that has no volume, correct? You'd have 4 pieces of metal. So it's got to be less than 10. Algebraically, what I'm doing here is I'm making this equal to 0 also. Do you see that? And if I make that equal to 0, then I get x equals 10. So that's my domain. That's going to be very helpful when I graph. It's going to be very helpful because some of you will want to write down 21. Why? I don't know. Maybe 21 is your favorite number. Maybe you've been following me on Instagram and found out I got to wear the number 373 Saturday morning when I did the Snowflake Shuffle. Some people ran the 5K Snowflake Shuffled. You know what I did? I shuffled. Because that's what I thought I was all about. It took me 58 minutes, 22 seconds to shuffle 5K. I came in last. And there's a picture on the internet somewhere about it, but I didn't keep it. All right, I'm going to stop right there because the bell going to ring any second, do you think? We had connections. They're going to take 10 minutes from first. Should I just keep going when the bell rings? Should we look at the graph? Yeah, what the heck. We might as well go. It's just more work time, right? You guys had, Nick had put all of his stuff away, organized everything, and then I'm doing this. Sorry, Nick. Nick, I'm going to type it in this way. X parentheses 20 minus 2x parentheses squared. Do you know why I'm doing it that way? Because it's a lot less to type on a calculator. And I goof up every time I type more stuff. I know what it is because I wrote it on a piece of paper expanded. But graphing, it's kind of nice. Now, I'm going to go to my window, and I'm going to go from 0 to 10. That's my domain, isn't it? Right? Now, I have no idea what my volume is. So I'm going to guess. And I'm going to type in 500. And I'm going to draw. And I did not go up high enough, did I? Right? You see that? So I'm going to back up here. Exit. Oh, actually, I'm going to go back to my window. Exit. Back to my window. And I'm going to put in, oh, let's go 800. There I go. Looks nice, doesn't it? Right? Now, since I got the time, is there a change of concavity? Okay. It starts out as concave and ends up, do you see that? Okay. I'm going to show you something else since I have time. I'm going to change my window again. And I'm going to go to 15. Ooh, it even hits 10 and bounces up. Now, I thought you couldn't go past 10. Well, those would be negative sides, correct? And since you're squaring them, it's going to be positive. It doesn't exist, but that's what the function looks like, right? The function is only a real shape within the domain of 0 to 10. Does that make sense? But when we do some calculus, we're going to come up with two critical numbers. Does everybody understand that? And I wanted to show you that graph of why we did that. So anyway, the graph looks like this. Here's 0 and 10. Now, is that a beautiful graph? No. It doesn't have to be. It's pretty close. Okay. There would be worse ones, right? And it has a minimum, and I'm going to make a table. And my table is going to look like this. And I'm going to have x over here, and I'm going to have v of x over here. And sometimes I think it's helpful for you to understand that this is inches and this is inches cubed, because you're going to be required to come up with your labels. Because I'm talking about volume, Jeremiah said it's length, which is inches, width, which is in inches, and height, which is inches. So it's going to be inches cubed. Does everybody understand that? Okay. And then I'm going to put some numbers in here. Now, does everybody understand why I don't put 0 and 10 in there? Because those values are what? 0. So I put those numbers in. I just went to the table part of my calculator and I came up with this. 324, 512, 588, 576, 500, 384, 252, 128, and 36. Now, why would I do that? It looks like my maximum volume is around 588. Would you agree with that? I cannot put down 588 as my answer. Do you understand that? Brian, do you know why I can't put down 588 as my answer? Exactly. It's like I paid you $5 to say that. Because I didn't do any calculus, am I? This is a calculus class, correct? It's not an algebra class. This would be okay in algebra. You know, if I'm 7th, 8th, 9th, 10th grader learning algebra, they probably, Ms. Monet and Mr. Karshi probably accept that. Because it's a pretty good estimate, but we got to do calculus. In other words, right here it says do calculus. So I'm going to take the derivative, v prime of x, because it's the derivative of the volume, and it's going to be 400 minus 160x plus 12x squared. So what did I do? I took the derivative of that volume function. Why? Because I'm trying to find the maximum volume. And we will see you tomorrow, and we will be done, and we'll have plenty of time to work tomorrow and Thursday. Excuse me, tomorrow and Wednesday, because today is not Tuesday.